Hello, how are you? Good. I don't know if Edu is here, and I don't know if he wants to say anything today about. No, he's not. Hi, Clement. Nice to see you. And hello, everyone. Tatiana, Ivan, etc. Okay. Before we start the class, a couple of things. I'm gonna be. I have a cable length problem here, so I'm gonna be looking at my screen mostly because I cannot be facing you, but I'll try to compensate or combine a little. And here as well, I'm gonna start my video. I've been reorganizing a little bit the documentation. Here, if you go now to weekly classes, there's an index of the different weeks where we put the assignments, the content, and extra links. And below, you also have some direct access to the classes that I've been giving here for electronic bits and coding and stuff like that. And specifically here, you have the ones about electronics. And today, we're going to do two things. The first one is that I want to talk a little bit more about what we started talking last time is the electronics production week. I want to, let's say, complete what we were talking, say, a broader sense about microcontrollers and then I hope that that is like maybe 45 minutes, 1 hour, and then half an hour about components, and let's say some doubts that you have regarding circuits and electronic design. The idea for these classes on Thursdays is specifically for the electronics. Sometimes are not going to be as, let's say, coordinated with the week or the week purpose in general, as they are, for instance, the other ones with 3D printing or laser cutting. But they're going to be like their own path, because I think that we teach electronics backwards, and I think there are a lot of things that if we teach them in a different pace, it's gonna land easy. So last time, I think that by trying to combine electronics production and the knowledge of microcontrollers probably was a little bit confusing, and I want to retouch that, and then talk a little bit more about some components. The idea is that these classes on Thursdays, I hope that over time we are able to make them more as say a session in which we talk electronics and you also feel comfortable asking questions about circuits or components or designs that we make, and not only me giving you all the content, but in general, that is hopefully compensated on Wednesdays. Okay. So here in the electronics, if you have a look at what well, this is the sequence of what we've been doing. The physics behind electronics is what we did in electronics production on Wednesday, very briefly. What is a microcontroller and what is a programmer is what we talked about in electronics production on the Thursday, but that I want to retouch a little bit that. Microcontroller summary is just where you have to go whenever you are lost with, I don't know what microcontroller this is, what family this is, how I program this, what do I need to make, etc. And the next two are Eagle and KiCad. KiCad we saw it yesterday. Eagle is, let's say, another now proprietary software for electronics design. And finally, here advanced electronics components, which I hope it's not like a class, but more like yet another page that you can go and see or find information about different components. I want it to be like more like a hub where we keep it going with circuits, components, best practices, information, rather than just being a class that we sit and that's it. Okay, so it's like trying to make this evolve a little bit and also have that knowledge that is ours. And after that, we can always refer and find information here, how to do, best practices, etc. Is that good? Yeah. Okay, so regarding this, I'm gonna go on the what is a microcontroller again. You see that this has changed a little bit, and that there's a lot of more information before uh, what we talked about 2 weeks ago. And I apologize for that because I didn't have enough time to prepare that class, and now I think it will make more sense. So I just want to re-talk about some concepts again. And also, please refer to this whenever you want to either reuse this material or revisit what and why we use microcontrollers, what are they, how are they composed, and what is the logic behind them. Okay. So if you agree, I will start. And for started, what I want to do with you is an exercise of how did we get to microcontrollers and electronics of today. And the idea is more regarding how do we represent physics, how do we represent information with physical phenomena. And I mean by that, that how do we use, let's say, electricity, voltage, light, etc., to represent information in some sort. That, for instance, I have a question for you now, is that using this very simple circuit, this one with the little fan, how many options, how much information, imagine that I want to represent information with this circuit about something, how many options do I have? Or what possibilities do I have to represent information with this? How many options? Information, something. Imagine that I want to say whether or not there's someone in this room, and I represent that with an LED in the corner, or with the fan being on. So how many possibilities do I have? Two options, right? So I have the possibility of the fan is active because I press the button, or the fan is stopped because the button is not pressed, right? And that brings us to the basic idea of representing information with the binary model, which is either there's something or there is not that something. Either we have an event, or we have voltage, for instance, if we translate it already to electronics, or we don't have it. If we wanted to, let's say, expand that, we can start talking about combining circuits like this and using, for instance, an array of the same circuit and trying to represent more information or more possibilities with that status of the fan or with LED that is on or off, right? And that is what brings us to the concept of digital logic in an analog. We want to represent physical things, but that are not possible to be represented with, sorry, we want to represent things or information that are not physically represented in the idea of binary. And for that, we have to combine it. And this is easily seen, for instance, in this, I think it was you, Mark, last time, or someone else here maybe, that said, okay, well, this is like an array of switches, exactly. Yeah. So the idea of, okay, I use an array of switches that they are only able to represent two possibilities, on or off, true or false, high or low. Again, it's always the same. But by the fact that I'm combining them, I'm able to represent even more information than just two possibilities. The whole array is helping me to represent. Uh, in fact, the rule of the thumb is if I have one switch, I have two to the one, so two to the power of two to the power of three, to the power of one, and that brings me 2, 4, 8, 16, etc., etc. Right? Now, this can help us also to make information that is analog in the physical world. Like it can be any possibility from 0 to a million, or between -10 to 10, to represent it with this sort of arrays as long as we follow a convention. And we, let's say, digitalize or discretize the analog world into the digital signal that we are able to represent using these conventions that we created that by combining little switches, we're able to give more complex amount of information. And we talked a little bit about this idea of when I have, for instance, this signal, this sine wave, I can use 2 digits to represent it, and somehow I have to put the signal into buckets, let's say, or bins, in which I say that any signal that is between this level here and this level here, I'm gonna just say that is 0, 0. Signals that are between this level here and this level here are gonna be 0, 1, etc. The more numbers I put, the more reliable I can represent that signal, that information in my electronics. And even if I put a lot of numbers at the end, it even seems like the real version, even though I'm just using zeros and ones. Right? This idea is like, does it make sense? This idea of I'm using just little some phenomenon, like physical phenomenon, voltage, to represent physical or information, and by combining a lot of simple possibilities or simple actuators, I'm able to represent complex things. Yeah. Then we talked about also logic levels, and now before we jump into microcontrollers, we have the core component of this one. Yeah.
Yesterday, Neil talked about transistor and Mosfet. Yeah, what is the difference? Because I think that's explained.
There is a difference. Mosfet is a type of transistor that they have different composition that allows them to handle much higher current in the outputs with very low, let's say, control in the transistor. So we can think of as a transistor as a switch, but that is electronically controlled. It's like a relay, a switch, interrupter, but that we control electronically. A transistor, you can see the importance in this because here I have to manually switch each of them to be able to represent the information. I have to go to each of them and 1, 0, 1, 0, okay. And now I have the information represented. But if I am able to represent that electronically, then that information can flow and I can make operations with it, and I can store it in memory, and I can have more complex setups with the use of electronics without human input. Now, the transistor is, let's say, the core component for that. It has this symbol, and by its construction, the idea is that we are able to control voltage, let's say, high or low, with a command from the electronics for our Arduino or a digital output. In a transistor, the output that I'm able to handle is of the order of the input that I have to put. It can amplify a little bit, but not very much. A Mosfet is much more powerful and can control very high voltages and very high currents with very low inputs. And that's why we call it like an amplifier. You can amplify a signal, an input that comes on one side on this part gets amplified on the other hand. But not only that, we can control and use that electronic switch to handle or to stop very high voltages and currents. And for instance, they're used to control motors. And that way we can say turn on or off the motor in a very fast way. Okay. So it's as if I was using a tiny electronic component like this, of this size, very small, but that can handle very high currents, and that I can control with an Arduino with a signal from 0 to 5. Does it make sense?
It's still on off.
Yeah, the output is still on off. We will see something, and you know this very well, that is called PWM, which is basically trying to simulate a signal that is on and off very fast, say, and by regulating the frequency in which I on or off, I'm able to simulate an average voltage that in this case, it would be 2.5 because I'm on and off the same amount of time. I have 2.5 as a voltage on average. And that helps me, for instance, to regulate the speed of a motor or to regulate the speed of a fan or, yeah, or whatever other thing. Because the motor is too slow to start and stop because it has inertia. But since we are not injecting full, let's say, power all the time, it doesn't rotate as fast. And by reducing the amount of time with this technique called PWM, we are able to reduce the speed. PWM is pulse width modulation, which now it makes sense because you're sending pulses and you modulate the width of those pulses. And by that, you manage the voltage level, but it's only on and off. You're not able to do, or the Mosfet is not able to be in a middle state, or at least not in the state. The component is Mosfet.
Oscar,
Sí.
open the email that they sent in the chat.
Here. Well, the purpose was not to talk about PWM in this class, but here is an example that Edu is sending. No? So you see that we're always talking between 0 and 5 volts in these two examples. And what we call duty cycle is, let's say, the ratio between the time that I'm on versus the time that I'm off. So I have 100% means that I'm on all the time. If I have 0%, I am off all the time. In between, you see 25%, 50, 70. And on average, the red line represents how am I on average, let's say. And in the 0% duty cycle, it's as if I had a 0 volts because I physically have 0 volts. In the 50%, I have 2.5. 25%, I have 1.6, or no, 125 or 375. No. That is more or less the idea, but it's always on and off, and that's it. So the idea is that with a transistor, we're able to control with a very small current in this part on the left-hand side, we're able to control very large currents on the others. And transistors, as you can imagine, they are the workhorse and the most important component in electronics. It's the most used component in electronics, and they are able to make what we call logic circuits. Now, let's start talking about it. What happens if we use circuits like this one, so simple as the one before, that it's only able to represent a 1 or a 0 if I connect the battery or not? What happens if I start making circuits that are a little bit more complex that can represent information in different ways? For this, there are two main concepts that we have to know, or two types of circuits: combinational circuits and sequential circuits. Combinational circuits, they don't have any memory, let's say. They are not aware of the state in which they are. You have an input and you have an output. And that's it. There's no state. There's nothing that the circuit knows about what is happening. You press the switch, the light turns on. But there's no intelligence or no memory about, oh, the light was off, but they turned me off. No, it was you put an input on one side and the output comes on the other, and there's no state or memory or awareness of the circuit of how it is. This, for instance, is used in amplifiers, signal processors. For instance, this is an old Marshall amplifier that basically takes an analog signal on one side, amplifies it, and it doesn't care if you used it yesterday, if you used it 1 hour ago, if it's too hot, if not, it just amplifies the signal and that's it. Is that more or less clear? On the other hand, you have what we call sequential circuits. And I think that you can see this very clearly in here, which a sequential circuit is basically aware of its own state. Oh, God. It's basically aware of its own state, and the state of the circuit works as an input. It's like as if the circuit had memory, and you could store something in the circuit.
It's not the feedback loop.
It's not a feedback loop, it's just that the circuit has some sort of memory. And well, we'll talk about this, but this is like the basic block of writing a program on a computer. For instance, you write something, you put a state or a code or a script that modifies internally the circuits or the status of the Mosfets or the transistors, etc. Turn some transistor on, some off, you write that in memory, and then when you turn on the circuit, it changes, and it doesn't work the same way as if you didn't have that state in the circuit itself, because it does something different, right? So this means that using electronics, we could do something that is dumb, that it doesn't have intelligence, or that we could use it for something that is a little bit more aware of its state, and that we can put things inside that modify the behavior of our circuits. And you can see how important this is, because all of a sudden we can do this, we can do work, we can make circuits that work for us, and that can start doing complex calculations. For instance, we can use or make use of logic relationships between switches or truth tables. At the end is 0 or 0 or 1s or 0, etc. To make, for instance, a circuit that is able to perform addition. And what we addition, like a sum of 2 digits. So you input 2 or 3 digits, and it's able to give you the sum of those digits. Because we combine different switches that internally are wired, so that when there's an input on one side, they give you the output on the other, that is the sum or the addition of those 3 digits on that you input.
Sorry, I think that I understand the concept of these two different the combination of these ways and simple. One would be a combination and one would be a
Combinational is, for instance, an amplifier,
okay.
A noise record, sorry, a sound amplifier. A sequential is any computer that you see every day.
Combinational circuit, they can make logic also the and or
Yeah, but these building blocks, sorry, these are used in combinational and sequential. Yeah, and actually these ones, these are more combinational than sequential. I didn't say that.
So if you have, for example, a circuit with I don't know, something that understands humidity, so like something with the sensor for humidity, that would be.
What do you do with that? You have
Okay,
an input.
understand if your water, if your plant needs water, or understand how much heat the air to.
If you use any type of microcontroller, or the circuit is like has the input and executes some code or something, then that is a sequential circuit for sure.
Oh, okay.
So at the end, what if don't worry about this. This is more like here I press a button and something happens, and every time I press the button, something happens. It's always the same. It doesn't change. But here, today I press the button on the Arduino, and the LED turns on. By tomorrow, I change the code and I press the button and it doesn't do anything, because I changed what I've written in the electronics, in the circuit, in the microcontroller, that, as we will see in a second, is a bunch of transistors that we are able to put information into that changes how the circuit reacts. But if you think of it, what we are doing is this, for instance, is an adder. Full adder is just you get inputs A and B, and C is the sum of them. All this is just part of, or these are, let's say, physical components that can be big, and this, like, that you can see them, but what we've managed is to make that integrated into small packages, and then we've managed to put a lot of them into microcontrollers, and at the end, we're able to make very complex operations inside a tiny chip. And that's the whole point. At some point, especially like this is the Apollo guidance computer. We went when, I don't know, when we went to the moon, we had this computer that was calculating the trajectory based on fuel intake, trajectory, weather conditions, etc. And there was a moment in which they started designing circuits that, if you think of a transistor, something like this. So this is a transistor. Imagine that you want to combine a lot. This is a switch, one of those switches, okay? From up here. From here, this is one of these switches. But you control it electronically, and you want to combine a lot of them to make operations and calculate when you are on outer space, because you don't have time to do the calculations at hand. You want to do that in a computer. Imagine the amount of transistors that you need to do this is of the order of hundreds. If you put 100 of these, you need a huge room to make complex calculations. So at that moment, the engineers, electronics engineers that designed this computer decided that we are not going to use these components. We're going to put them in this integrated, what we call integrated circuit, which basically contains the same as this, but in this tiny package.
One is one transistor, other is several.
In this case, I assume there's, I don't know exactly, but the idea is that this is an integrated circuit that may contain a lot of them. So now these integrated circuits, these were the first ones, but now there are a lot of flavors, and you will see them as this one, like here, that have different packages and different formats. Some of these you see that are like very similar to what I have in my hand, but basically all of them have different interactions or number of legs that internally have the same components or very similar. What we were talking about yesterday when we were doing electronics design, you remember that I said these are HTTiny, SOP, TSOP, SSOP, etc. These are the packaging. TO252. It's a type of packaging very commonly used in Mosfet. You will see it here. SOT223, common packaging using regulators. And don't trust the packaging, because sometimes the same packaging or the same shape can be many things. This could be a regulator, could be a Mosfet, could be, who knows. Of course, if you if you have a lot of legs, very likely that's a microcontroller or something like that, but it doesn't have to be. Okay. And inside of this, on a microcontroller, at the end, what we have is this. You have these little legs that are what we see or we interact with. And inside of here, we have the actual silicon that we managed to put millions of these inside. And these little legs are gold eggs or golden legs that communicate these legs to the inputs of the microcontroller that internally have these in millions. And to just show this, I'd like to have a look at this video. And
configuration of in this case microcontroller using this kind of system.
people that have not this, but But you see that it takes like a huge room, and you can put LEDs and etc. And you see, actually, one of the circuits that you have been doing, while I talk, you can see. If you look at this board that we did in the academy, sorry, the academy this is a sequential circuit. You power it. If you have an resolution somewhere, let me grab one. It only gets power. So you see, it's still going down, and it will take forever to get there. So this gets only plus or minus, so 5 volts here. Okay. Actually, I could do it. I don't have a mini. Okay. Repeat power. The idea here is that here I have what we call an OR gate. No matter the switch that it has, the LED comes on. Okay? If I touch both, the LED comes on. Here I have an AND gate. And here what I have is just, well, it's not even that, but it's like as if it was a transistor, the combination. Here I have to press both. You see that if I press only one, it doesn't work. But if I press both, the LED comes on. You see the power of this, because this switch is not, okay, now I'm pressing it. But the idea is that we replace this switch by the Mosfet that I don't, or the transistor that I had at hand before. And we control it electronically. If you do this, then you put a lot of them, a lot of these tiny circuits. You make complex logics of, okay, I have 10 buttons and I put them in cascade. At the end, you could end up putting that very, very tiny and end up with a city. It's like, for me, it's like a city with different streets and roads and buildings going from one another, going deeper and deeper. That's the scale of microns, so not even a hair. And each of these are connections to small transistors or small, tiny, electronically controlled switches that we can modify and write things onto. Yeah? The idea here is that at some point, computers became programmable. And you see this, like they started connecting, making connections with cable in the past, and computers were the space of a huge room. These are some ENIAC pictures. The first picture is it's the original, like it's the full room version of it. Okay, so without microcontroller. Exactly. It's like a microcontroller, but the picture room, a macrocontroller. Then the same, and the idea that the programming was done with cable. But at some point, the microcontroller kicked in, and the people at Intel developed the 4004, which was the first microcontroller in history that contained hundreds of transistors in this path. In which we were able to not only do these tiny things like the people in the Apollo, but do more complex operations and write into them, and they will be stored as a sequential circuit that later on we could execute orders. At the beginning, they were used for printers, finally. So it was, if you read this article, it talks about how these integrated electronics were used for printing, the printing machine. But now you can imagine that they are everywhere. And probably Neil has shown this image, which was the amount of transistors. So again, I don't know, they are the amount of these components that there are in a microcontroller. So you had order of thousands in the 4004, and this is a logarithmic scale. So you can see that the latest super high-end microcontrollers today, they have of the order of billion micro transistors inside. All of them wired inside, and with not only the possibility to do these stupid things, but also to write things into them and store programs. And that is where we left it, let's say. The idea there is that these microcontrollers now, we are able to define what a microcontroller does, let's say. And we then, we went then talked a little bit about more the idea of classing the microcontroller and what we use the ISC for, which was, okay, now we need a tool that allows us to write into those transistors inside and modify the circuitry, let's say, and modify the state of the microcontroller. And that tool is called a program. That is what you did 2 weeks ago.
So you say that the transistor takes state and
yeah.
If there is no electricity at all, they all have the same state. And so how do we store our program inside the chip? Because every time you remove the power source, everything goes back to the same state.
Yeah.
How do we store it?
Well, so there are some special types.
Oscar, sorry to interrupt. Can you repeat the question that they just asked? Is it possible to do it?
So you were saying that how do you store a program, for instance, in a microcontroller or in memory, let's say, if what you need to use is power or power input to modify the status of the transistor. But when you remove the power, then let's say the transistor is off and there are no information. You have the answer, Edu?
I'll let you answer that.
It's not as simple. So the idea is that memory, so the way that you store things in a computer is not only used with these kind of things, but there's hardware that you can modify once and then it remembers afterwards. And you, let's say, charge the transistor, and in memory, I'm not going to be able to give you all the details, but that stays, and it's not as simple as this. So you can store things in, for instance, non-volatile memory when you remove power, because you physically modify the component. In this case, the idea is that, okay, you have to, or for instance, on the initial computers in which you only had this component, you have to physically wire and physically go with these suitcases with wiring that you put into the computer, and that was the problem, letting current or not onto the different parts of the computer. Now that memory, let's say, is something that you have to be able to physically modify, either because you burn it with a floppy disk, a CD, or something, or because you use another type of semiconductor technology that allows to store that in the state because you burn it, and it's not like just on and off. So it's a little bit more complex, but the idea is that okay, so this comes to the idea of this. And this is a bit more complex, but the idea is that you have something in memory written that stays there forever, let's say, until you erase it. That is not made out of the circuits. But when you first power your electronics, when you first give power to the circuit, there's something called bootloader that takes that memory and writes it into the transistors of the microcontroller and transfers that into the circuitry here, loads everything on boot, that's why it's called bootloader, moves that code, wires it, and then stops the bootloader section and starts running with this new state that internally in the microcontroller is not permanent, but it has to be transferred when you first power it from the memory to the circuit. That's why, and this is not the objective for this, but the bootloader, if you read a little bit about this, is basically taking what we call the flash section, which you burn with in memory, you put your code inside, and when you first power it, since the state, as you say, of the transistor is not permanent, copies it, and since you have power, you are able to wire it. And then anything that comes already goes to a circuit that is already prepared.
So it's not the component, it's not a transistor, it's something else.
The memory is something else that I'm not going to be able to explain now, but
it's not a specific transistor.
Exactly. But inside, the idea is that okay, when you flash or you wire at the beginning, let's say, you have to physically wire components. Then you are able to write things into the circuit, but only when it's powered, because you use these things. Now, you remove power, but you have memory that is loaded into the circuit by this thing. Yeah. Okay. Do you have more questions? Do you have some doubts from yesterday? If not, I'm just gonna skim through the next part, and then maybe we can talk a little bit about the assignment itself.
Okay.
Okay, so here in this part of electronic components and circuits, I would like to again have this as a live document where we put references on documentation on components and circuits that you might implement on your own designs. Here you see that, well, there are two parts, components and circuits. The circuit part is a work in progress, but the components already has a lot of information. We already talked about many of them, but some of them at the bottom are, we didn't talk about it, especially here about some questions about Mosfets. Maybe we can talk about it. And the idea is in the future, well, you will see that they all have the picture, description, and some interesting readings that we've been compiling through time. And at some point, we might also include some examples from the inventory so that you are able to find that component in the inventory and then use it or relate, okay, I need a regulator, which component is it? And, okay, you go here and then you find it all. For the first ones, I would like, since you are already experts, maybe you can talk about resistors. Why do we use, or what's the purpose of a resistor? Maybe someone can explain. Sorry, to limit resist current to limit, let's say, limit. Okay. Okay, and when we do that, what happens? So we limit the current, but is it for free, or does it happen at the cost of something? We release it. So be careful with these things. Normally, the voltage that we're going to work in the currents are very small, but consider that some of these SMD components might not be able to dissipate all the energy if you have a huge motor or something. And sometimes you have to go into this thing and they even might explode. So these components, if you go into any resistor datasheet or DG key component, you'll see that it has rated currents. And actually, I will put some comments in here about things to take care about. In this case, the most important, not only the resistance, is the rated current, which is basically the amount of current that you can put through the resistor before it releases too much heat on it. Of course. Yeah. No, at the end, just think about yesterday's schematic design, say. In the schematic resistors, they don't care if they are SMD, if they are through hole or whatever. At the end, you decide. Right? And what you transfer into the design of the PCB could be SMD, through hole, these types, which are through hole, or however. And it's not an uncommon practice.
Power dissipation, you don't decide on a schematic part.
I mean, if you are making a board that has, let's say, high currents, and by high currents we are talking about 0.5 amps, 1 amp. 1 amp is already significant current. Then you have to start taking care about those things. Normally, SMD components below 0.5, they are going to be okay. Well, some interesting resistor readings. You have here this thing of the color code. I already assume that you are experts in this, that you can just Google a calculator and you will find that there's an explanation to this color code, the different bands, specifying not only the value, but also the tolerance, how much tolerance does that value have. And here, for instance, you already have a calculator. You'll see also that the resistors, the SMD resistors, they don't go like this, but they go with a code on top. Edu, do you have one tool for that? I didn't remember to put it.
Tool for the resistor code? Yeah, there is. I think it's in that documentation. It's around there. It's not in the page.
Oh yeah, I have one.
I have one in the chat right now. Wait.
Okay.
Yeah, here. There you have.
Okay. So you'll see that. Thank you. So you see that the SMD resistors, they look more like this, and that they have, I don't know, 3-4 digits. And it's not this is not a 102 resistor or ohms resistor. There's a code in this. And normally, the two first digits are, let's say, the value. So this is 10, and this is with 2 more zeros. So to the 10 to the power 10 times 10 to the power 2. So 10 times 100. For instance, if you have something like 4990, that is 499, because you have 499 and then times 1. 4991 is 4.9 or 5 kiloohms. 2, then you can imagine, etc., etc. Be careful about this, because you might see 490 or 49. You think that is something that is not. For instance, 49, I think is 49.9. No, 499, 490. Yeah, 490. Sometimes I made this mistake, is 49 ohms, and I thought it was 500. Okay. So have a look at this. I'll put it in the same page. What else? Other components, capacitors. What do we use capacitors for? Can someone give me a hand? Filter. Yeah. What else? What do you say? Store, but forever or for how long? For let's say a very limited amount of time. But yeah. I'll put some circuits here for now. The one that we talked about yesterday is the most common one, but basically it's filter noise. Capacitors, as you see, there are millions of, well, not millions, but many different types. The most common ones that you're going to see are either, I don't think you will even use electrolytic, maybe. Be careful with these ones because they have polarity. So you shouldn't connect them the wrong way. You identify that because they have this band here, the white band is the negative, and it also reminds you with this sign, it's a minus sign there. But normally you will use capacitors that look more like this one, SMD capacitor. That look more like that. Yeah, especially these ones are the most common ones that we use in the academy. They are ceramic capacitors and they don't have polarity. So you can connect them either way. They don't have a number on top normally. These ones do. These ones they do have, and you also see that they have a band. These are not ceramic capacitors. Uh, they also have the number on top and they have polarity. But these ones here, they don't have polarity. They don't have a number. So please don't mix them. If you grab from some box and you change them, then we are not able to know which ones unless we measure them. And it's not easy to measure it with the multimeter as well. So you can measure it, but it's not. Capacity is a very tricky thing to measure because if you put it on the table or you touch it or something, this capacity changes because as humans, as materials already hold some capacity. If that is not perfectly isolated, it's not easy to measure it. And normally the multimeters here, now we have new ones, but they have been used for a long time. So it's not always so simple. So if you mix them, it might be that you just don't know what.
I have a question about this. How do you I'm thinking about something that maybe the band, the piano, the toys, that was a capacitive piano. So you were able to touch the tubes,
Yeah.
and they make the song. So I was thinking it's a similar way of like working as a regular capacitor.
Yes and no. So, okay, let's understand a little bit what capacity means. No? Maybe we can use I don't like it that much, but we could use this water analogy. That is like I have this bucket with water, and I put water in, and I take water out. And this volume here is like accumulates some water and more or less makes this output. Let's say this output here is irrelevant of what you put inside, right? Because you accumulate it a lot, and more or less you always have the same here, and no matter what you do, right? Every object and every material has capacitance. So there's a capacitor versus capacity or hence, which is this is the component and this is the property. Earth, planet Earth, in itself has capacity. It's able to store some charge. At the end, what we are doing is accumulating some difference in voltage here and there, and by that we accumulate a little bit of energy. Planet Earth has around 1 farad of capacity. These components have 1 divided 1 by 1 million farads. So they have a very small capacity, and the amount of energy or charge that they are able to store is very small. So this bucket at the end is like a bucket like this. That is super tiny. So it empties, if you open this too much, this bucket empties super quick and it's not ideal. So it's not ideal for big battery or big capacity. They don't work as batteries, they just can store a very limited amount. And the example that you were talking about goes into the idea of that every object in the universe has capacity and has a capacity and has the possibility to, or we have the possibility to measure that by doing something like, imagine that this is the tomato, a blue tomato, and you connect one wire on one side and take one wire on the other. And you imagine that if you send a signal here, like that, it has to travel through the material. And depending on how big this bucket is, it will take more or less time to be seen here. Imagine that here you put like a huge shot or jet of water. You might see it here or not. And the same way you will see this peak here through the material and you will see it in here, right? At some point. If you measure the time that it takes to go from here all the way through the material and here, you could have that as a proxy, let's say, for how big this bucket is. If it's like that, if it's like that, if it's like that, or if it's like that. Right? And basically, when you do this type of project, you use what we call capacity extension. You basically do this process. And since this is since every material has capacity, when someone comes and touches the tomato, the time that it takes is a little longer because basically it has to go from here, maybe goes through this finger, comes back, and goes over there. And this you're able to detect it. Chris over here is an expert in capacitance now. He has a PhD in capacitance. But basically, that's it. So capacitors, we use them for that, for the purpose of filtering, because you can see that if this is like this, then this is very easily going to be like a constant unless this is empty. So we use them for filtering. But we can also use the capacitance of materials to be able to make this type of thing. With this smart idea of sending a pulse on one side and getting it on the other, and being able to detect how that changes when something that also has capacitance touches it. Yeah. Does it make sense?
Today, said that the normal capacitor, the polarized one, use them. For example, the higher voltage. Why the other one cannot do what the polarized one is doing?
I think it's that I'm not sure. I would be lying, but I would imagine that is a matter of size, like amount of capacity that you can store in a ceramic capacitor versus an electrolytic one.
And we cannot make the
Exactly. That's what I think. I'm not sure about that. Maybe we can think like research it, but I honestly don't know. But I think it's like gasoline diesel type of problem. Like you cannot make a very small diesel or a very big gas. Okay. So what else? More components, capacitors. Here, capacitor wiki. We already talked about diodes. Here, I want to show you this one. So this page, whenever you like whenever you get COVID or you have the flu or a cold or something at home and you cannot get out, read this. Honestly, it is the best thing. When I did the academy, I got the flu exactly during the electronics production day. And I was feeling super bad at home and I got the whole thing. And this guy, even if it's not very nice, but he does like a lot of crazy things. He calls it concise electronics for geeks. But he also has some very cool projects. You can see the style, um, but it's super nice. And here it talks about every single thing that we've been discussing about components, electricity, why they work, etc. And he goes down to a very deep level into understanding diodes, Mosfets, transistors, etc. I really recommend this reading. And he talks about diodes as well. So do you remember what diodes were? They allow current in one direction and in the other, they don't. Okay, exactly. And we use that normally for protection. We use them as well. You'll see as rectifiers, sorry, as rectifiers at 8 bridges for controlling motors. We'll see that in output switch. And now I'm going to complicate your life a little bit because there's a lot of types of diodes. Actually, if you go here to the diode wiki, you see that diodes, they are not only, they allow on one side and they don't allow on the other. It's more or less that, but there's quite a few types of them. And here you have some in the wiki here, but you have avalanche diode, GUN, laser diodes, thermal photodiodes, Schottky diodes, Zener diodes, and blah, blah, blah. Two important ones that I want you to know. Number one, Zener diodes. You'll see this especially in applications that use USB or that connect to a computer. Why? Zener diode is the same as a normal diode, but it allows they allow a little bit of backward current. So they allow a little bit to the front, and when you surpass a little bit, so at what we call a backward voltage, they allow the voltage to go back, but only that voltage. So you can imagine that they're super useful for protection. And for instance, if I connect something to my computer and I don't want these electronics to affect my computer, I'm going to limit the amount of voltage that my electronics can bring to the computer and vice versa. And you'll see this in USB circuits because they normally are used as voltage protection and power supply as well. Schottky diodes, very also quite important. It's even, I think, more used than the common diode. And basically, they have the same behavior as the normal diode, but they allow current on one side, but voltage or current in one direction, and the drop of voltage that we have through them. So if you have 12 volts on one side, you have almost 12 volts on the other. If you have a normal diode, you have 12 volts on one side and then 10 volts on the other. Okay. So you drop, you lose some voltage there. Yeah, yeah, exactly. I was going to do that. Sorry.
It's like a resistor.
Exactly. So here, mouse, whiteboard. So a normal diode well, imagine this is it, right? Okay. Here you have, this is a normal diode. So you have 5 volts. And here you have your, I don't know, your resistor and your LED and whatever, your other circuit, let's say. And here you lose a little bit of voltage, maybe, I don't know, 0.3 volts. And you get here 4.7 volts in a normal diode because you lose a little bit here.
That's due to the original material used inside the wall.
It's the type of material that they are made out of, and the configuration of that material internally. The normal diode has some what we call drop voltage. You just have to assume that. That's why they are not normally used in common electronics nowadays. Well, they are used, but not in applications where you have very tiny voltages, like 5 volts, because you're going to lose already some. And if you have 5 volts here, and then you have 4.5, your electronics might not even work. Okay. So what you use is the Schottky diode. And if I don't remember, they have this shape. Let me cheat. Schottky diode symbol, I don't remember. Here, yes, they have this squiggly thing, you see. Where did it go? Sorry. So they have this shape. This symbol, it has that little, like, I don't know, whatever you call that. And the voltage that drops across them, if in the other one was of the order of hundreds of or tens of millivolts, here is really, really small, and here you have 5, and here you have 4.999. They also have an advantage, and is that they can turn on and off very fast. So they can, if you put some voltage here, and you, for instance, want to put, and this oscillates between 5 and 0, 5 and 0, 5 and 0, they are able to reproduce that in here as well. In a normal diode, instead of this, you would maybe get something like this, because they don't have that fast shifting. So you'll see these ones normally, and these are the ones that we have actually in the inventory. Most of them that are that look like this. Like these ones are the most common ones. I think if they allow 12 volts and 2 amps. I don't remember well, but something like that. Oscillators, we talked about them the other day. Piece of material that is able to generate a periodic pulse, and that is like the director of the orchestra, that gives, like, or the metronome that teaches you the pace or the pitch, let's say, when you are talking the guitar or the piano. For the same with microcontrollers, much faster. They look like this. These are made out of quartz or other piezoelectric material, but there's also some other ones that are called resonators that I didn't show them here. Sorry, but Resonator electronics looks a little bit more like no, wait. What's this name? Resonator, like this one. It'll look a little bit more like this. These are a little bit less precise, but they are a little bit smaller. So for these ones, the way that they, oh, sorry, I don't know if I was showing. Sorry, I'm talking about this component here. I stopped sharing the screen, I'm sorry. So this is a resonator, and this one here is an oscillator, let's say. The resonator, just as a reference, you'll see that normally this resonator has two legs, and you have to put, I don't remember, capacitor. Edu, help, I don't remember.
Tell me.
El circuito, un oscillator, ¿te acuerdas con los capacitors? Era de salida a ground, sí, ¿verdad?
Sí. Tiene que tener un bridge de ground.
Exacto. So, era, lo estoy haciendo bien, ¿verdad?
Sí. Sí, sí, perfecto.
So, this is ground, and this is ground. And in this one, so in this oscillator, you need to make this circuit. Okay, it's exactly, it's the output, let's say, that is in red in here is what you're going to input into your microcontroller, and that is going to be the timing. Let me clear it, and I'm just going to make it again. So we have why I'm not able to draw now. So in this one, in the oscillator, and don't worry, I will put this in the documentation. Your microcontroller has two pins. Normally they are called X-tal for crystal, and crystal 2. Okay, these two pins, they go one and the other to the same component, which are these legs here. And capacitor, so that's ground, and capacitor. Okay. On the oscillator. On the oscillator. The other
where we can find some examples.
the academy, yes. So you will find if you go to so have a look at the academy. Let me show you not embedded programming. Okay. Have a look in here. This is what you saw yesterday with Neil. Sorry, I just don't want to delete this part. But here you have Hello Board. And in Hello Board, you have a million of examples that show you how you connect to that microcontroller. And there are a lot of examples of this microcontroller with a resonator, this one with USB, this one with a capacitor. I recommend that you skim through some of them based on what you want to do. Have a look at, for instance, I want to use 80TANI3216. This is my board. And I see that I have this simple connector with a capacitor here of 1 microfarad between ground and voltage, FTDI, and the programming. A more complex board, like for instance, a programmer, like the one, for instance, for this one. This is the typical power AST. It also has these Zener diodes that we were talking about before, because you have a USB connector. This is the same component as this one, the crystal here, the two paths for that, and the two capacitors, 10 picofarads, that go from the output, go into the microcontroller, and then this one goes to ground. I don't know how to move this, but believe me, yeah, goes here under to ground. This other capacitor goes from ground to voltage. And the frequency is the same, but now you understand this part. Crystal, this is the same one that we did yesterday. This one doesn't have an LED, but if you wanted to put a power LED, you could put it next to this this capacitor, the same circuit we saw yesterday. So, yeah. So I recommend you go to this one, and we'll complete in the page that I just showed you the different one, like different examples of the use of each component and typical circuit, how to control a motor, how to read a sensor, voltage divider, etc. But little by little, let's say. Yeah. So what I was saying is that this crystal oscillator has this schematic. The other one, the other resonator that looked like a band that has 3 bands, already has everything in the same package. But as you can imagine, you need then 3 connections. You need crystal, crystal, and ground. So they have crystal, ground, crystal. And they don't have polarity. The only important one is the middle one, that is the ground. Again, it's much simpler to solder. It's a little bit smaller, easier to wire and to design, but they don't have the same precision into the cloud. For the purpose of the academy, you're not going to have any problem. I mean, these ones, these resonator, the ceramic resonator, you're going to have no problem with the speed, unless that you're doing something super advanced with audio or, I don't know, amplifying things or whatever. But you can choose whichever one you prefer. Okay. I would recommend that you try both, so that you know how to design with both of them, and then you just keep using whichever one you like.
So when you connect that to the microcontroller, it knows that it has to follow this frequency.
No, you have to tell the microcontroller to follow, yes. And that is, we'll see in electronic programming, but when you program microcontrollers, let's say a microcontroller is not as simple to use like these ones that are already like for education, let's say, but that you are programming the core of this. You not only write the program, but sometimes you also write what we call registers, fuses, that are like internal switches that specify these things. Do I have an external resonator or not? Do I have an external memory or not? Do I have whatever speed for the CPU, etc. This type of things. And you write that, you send special commands that are something like the code, but it's not part of the code. And they are called fuses. We'll see that in programming, but we'll put that in resonator. Yes. They look more like hexadecimal code, let's say. So let's say you have a combination of options, right? One option is this thing or not, external memory or not, CPU, speed, etc., etc. Those different combinations, you translate them into, I don't know, a code like 1 through like that, and you send it to the microcontroller with the USB, and it goes, or USB or FTDI or something. Okay, this is less and less common, but we still use this type of things to get talent, especially with smaller chips. Okay, you are already experts on transistors. Basically, transistor is a small switch that is able to control a large current flow with a very small current. Mosfets, these are a type of transistor, is field effect transistor. It's a type of transistor. You have different types, BJT, bijection, bipolar junction transistor is the internal composition, let's say. This guy explains it really well. And then field effect transistor. Metal oxide something, field effect transistor, are the ones that we talk about here. Metal oxide is the important part there because it means that they are able to control very, very, very large currents, order of amps and tens of volts here, with orders of milliamps and like 3 volts or 5 volts in here, which is very powerful because you can control this whole room in lighting, for instance, or that a motor from the CNC with this thing. Okay. Last thing, we're going to finish, regulators. You'll see them in this package or in the SOT. I think it's this one, SOT223. Yeah, or in this format. We normally have this one, but remember these could be many things. And basically, the most common type of regulator that we use is called LDO, or low draw pad regulator. Basically, what it does is that if you input a certain voltage, so this is input voltage, and this is output voltage. At some point, they regulate. And for instance, if this is 3.3, and you input 5, you have 5 volts on one side, 3.3 on the other. And it's useful for adapting levels of electronics. You can imagine that your microcontroller, and you will see this in the ESP32, the Wi-Fi antenna with Bluetooth and everything works at 3.3. But from the USB, you have 5. So you put one of these, and the USB works at 5. I did this wrong, right? Sorry, it's here. You input a 5, and it always gives you 3.3. Yeah. Do they work in reverse? No. Before you ask it, they only regulate from input to output. So, and before the cutout or the cut voltage is linear. That this area here, it goes, if you put 2 volts, it gives you 2 volts. If you put 3 volts, it gives you 3, 3.3, 3.3, 4, 3.3. That's the idea. Okay? And you normally put this in the power area of your microcontroller, so that if you have 5 volts or 12 volts, then you can adapt it to 5 or 3.3. This is something for now, you don't have to think that much, but when you design your whole system for electronics, input, output, etc., you might be using one power supply like this that normally gives you 12 volts, and your electronics work at 3.2. So you have to adapt it. You cannot put 12 volts into this thing, and for this you need a regulator. Yeah. No, this no. This doesn't have a fast switching response. And is not good for your microcontroller either, because normally this is like a power input for a system, and microcontrollers don't like to have an average voltage like PWM. Those are for things that either move or that have some certain inertia, like either motors or, for instance, lights or LEDs that the LED still flickers, but visually you don't get it. The microcontroller will be turning on and off and on and off, and you will feel it. Yeah, and that's it. My only last thing to say is that really check this. My only recommendation. I really like this guy, and
I have a quick, like, probably it's a stupid question, but how do you think that when you are designing your board, you have to think how this is going to be connected to the other, right? So how do you decide that? I've seen, like, for example, sometimes we have two pins or five or five, like,
so first thing is that your board, you need to be able to program it. And the programming interface is gonna define how your board connects to the outside world.
and how do you define how are you going to, which is going to be the program?
You don't decide. If you choose a microcontroller, it goes with it. So each microcontroller has a programming method. Some of them have the ones that you made, UPDI, let's say. Some of them are programmed with SCI. Some of them are programmed by serial. It depends, but those are the most common ones. So you have to make at least a connector for that. That could be the same connector that you put also for power, or could be another one. For instance, it's very common that you, for instance, leave this header here for programming this one. This here for programming the microcontroller, and then this one, this big one, for power. This is up to 12 volts. And imagine that you have a power supply like the ones in your laptop. You connect it in here, but you don't program it in here, you just power. Why do you use this one and you don't use always this? Because this is not thought for high current, but maybe this one is. And you can control outputs with these levels of currents that this one is not able to hold. So it will depend on the microcontroller that you use, the programming interface, and what do you want to do with the microcontroller. It's just going to read sensors. Very likely you don't need this thing. With USB or something similar is fine. If you're going to actuate, for instance, move motors, then you need something a little bit more robust because there's going to be more current and it's unsafe basically, and not only for you but for the electronics. So you need another input that is, let's say, more reliable. And that way, that interface already, so your project or your idea defines how you interface with the board. Don't think of the board as just a microcontroller, but as what the purpose is. This is the main component, but it's not the most important, not the only one. This is the interfaces that you have with the outer world, and what it wants to do is what is going to define, for instance, that part.
And for example, the one that we were designing for making yesterday, for that one, we were thinking about the components and how they were going to be connected, but not about how to program the
No, how to use the program. Like as Edu says, works on, works off. But it's not about the interfaces that you use. This is either these classes and your own research onto the electronics and our support on helping you making that design. This week is for you to start digesting all of that, and for me and the rest to help you say, okay, you want to use this one. Have a look here. You need to program it this way. Do research. Yeah.
How do you choose your microcontroller? I mean, I want to create, I want to do something. How do I decide that microcontroller is the best one? Or if it's capable of doing that?
First thing I look at is inputs and outputs. It's gonna be, so if you imagine that, so what everything that we're gonna do in the academy goes through inputs, process, output. So for me, the two most important ones are input and output, which basically define how many pins you need in the microcontroller and what those pins are able to do. That's the first thing. Inputs, if you need digital inputs or analog inputs. We talked about this in the other class and before. Basically, is if you need to read just like zeros or ones, or if you need to convert an analog signal that can be anything, right? That will determine the amount of pins that you have that can read things in both types. Second thing is outputs. How many outputs do you have, and if they are capable of certain things. For instance, the PWM that we were talking about. Not all the outputs are able to do the same thing. Some outputs are only like on or off, and that's it. Some outputs can do this PWM, which is on and off and moves very fast. That does it in a way that seems, Edu sent this earlier. I don't know if you were already here, but he sent this image. Oh, sorry. This image here for PWM. No, not this one. God. This one. Okay, some pins are able to do this really fast on and off, and on average we have certain voltages that can hit something. Either the light is dimmer or brighter, or the motor is spinning faster or slow. If you look in an Arduino Uno, you'll see that some of the pins, even if they're all digital, not all of them have PWM possibility. They have like a little tilde. If you look in this way, you'll see already. And they have this little tilde, like the engine, that has PWM.
What materials they use?
Sorry?
What materials they use?
What the circuit, like
The interpreters.
sorry.
Something, what material they use for the circuits?
Normally has phenolic resin, like FR4 for the production. And on top you have like a silk screen. That is like in Spanish is serigrafía, more or less. That is just like a vinyl layer with some drawings that is thermally attached to or printed to the resin. So that inputs and outputs, more or less clear. That defines the amount of things that you can do. The ones that we have in the academy normally cover wide range of projects. You see the page that I showed in electronics production. You go there and you see the different maps and different possibilities. Last one, processing power. It might be that you find a good microcontroller that has enough pins, enough inputs, outputs, but is very small in terms of memory. For instance, some microcontrollers only have 4 kilobytes of memory, which is nothing. And the amount of things that you can do with that It's very limited. Around 32 kilobytes, that's good, big enough. More than that, 256 kilobytes is a big computer, and that is already like one of these mega or something like that. Depending on what you want to do. If it's something very simple, like just reading a sensor and sending it somewhere, you don't have a big program for that. It can be 10 lines of code. You can fit in 8 kilobytes. If it's the main processor of your electronics, and it has to do download a web page, show something, read a sensor, process it, post it, control a motor, in these libraries, things like that, then that is not going to be 4 kilobytes, it's going to be 100 kilobytes. But you need a bigger microcontroller. Okay. Finally, but for me, this has never been a limitation, is speed. Normally, the speeds of all these microcontrollers work good enough for almost everything we want to do, unless we want to use PWM or control model. Some of the microcontrollers don't go fast enough, or they're not accurate enough in their output PWM, and they don't make good motor controllers because they are not accurate enough, and the motors behave floppy. They vibrate and they don't interact well. So normally a microcontroller that works at 16 megahertz or more, it's already going to be enough, but it's not always as accurate. So something like an mega or things like this is already good. Examples, have a look at projects. Like if you want to make something like an Arduino, use something like an Arduino that's at mega, things like this. If you want to make a small board that only reads a sensor, and that's it, and doesn't do anything, or has an LED, and that's it, which is very small, you don't need that big thing, you need something. But at the end, it's input, process, output, and that's it. Yes. And always remember to go back to our little knowledge, let's say, pages. This one will keep going with components and things like this, but this one is your way to go for microcontrollers. And you have all the information on libraries, possibilities, programming methods, memory versus pins, etc. So have a look at this, and also I like to put a lot of links. So also we can, if you're planning, yes, there's a lot of research, but it's good. More things, more questions, or we'll call it for today. No, someone else over there on the other side. Edu, do you want to say something?
So, Oscar, what we have to do this week?
Invite me for a coffee. Okay, so this week is about designing electronics. You have to make what we call a hello world, or hello world is this first iteration of something, right? It's the first time that you do something.
Oscar, show it on the Academy page where it is, for example. One of the
yeah. This is. It was here. I have to put this. You see my screen, right?
Yes.
Okay. So here, always assignments. Well, normally the group project is that you test the equipment in your lab to test the operation of one of the boards that you design or a microcontroller. It could be from a multimeter to an oscilloscope that we haven't seen yet, but we will see. There's one oscilloscope in there, but mostly a multimeter always check continuity, check voltage levels, etc. Okay, you have multimeters here, and as far as I know, well, I'm not sure if anyone showed you. Did we show them when you were soldering, Edu, or not?
Just continuity.
Just continuity. Okay, so I'll do a quick round of this. Then the other part is remake or redraw, important, hello world board. Echo, yeah, well, Echo is like one of these boards normally you use to send something like send it a text and it will send it back. But at least what the requirement that we put, and Edu, correct me if I'm wrong, is that it's just a hello board that at least has a button or a microcontroller with everything that goes with it, a button and an LED. But the button is not connected to the LED. It's not a combinational circuit, it's a sequential circuit. So you have, you press the button, the microcontroller reads it, and then the LED is controlled by the microcontroller as well, not directly connected. You will need, exactly. You will need to program the microcontroller, but you don't have to do that now. You have to do it in electronics programming.
But then we cannot test if it's working or not.
If you want to do it, you can, of course.
Okay, no, we don't. Yes,
but the requirement is you program it in the electronics programming book. And the idea is that you test it with these things.
Basic microcontroller without I thought that the people like knows that this.
So guys,
Just pressing on the button and it's working with you.
just in today's class, do you see my screen?
Yeah.
Okay. So here you can come and let's see, for example, all the year example. Here you have like a student guide. You click on it, you will see this is the documentation from, I think it's 2 years ago, one student that is quite good. Explain a little bit concepts, but he went onto one of the Hello World examples. This is the basic board that you can find in Electronic Design Week, Hello World, and will automatically go to this one. Like for example, the 80 Tiny. Let's see the board. It's the same one. So you have this board that is 80 Tiny that has the basic components to make it work. We have some pins for programming, like pins for communication, capacitor, resistor, and resonator to make it work. So up to this board, we need to add a button connected to one pin of the microcontroller and an LED with its resistor connected to also the 80 Tiny. So in this case, the student took this example board and this documentation on how he actually designed it, adding the button, the LED, and then milling it to stuffing it and fabricate it. So there we have the final board. This was the initial board, and then this is the, let's say, upgraded board with just like 4 components: one LED and a resistor, a button and a resistor. So the point is, you can fabricate the basic one, or you can choose to fabricate other with other process microcontrollers. So these 80 Tiny 44, 45 are the older generation of microcontrollers. All of you have made the FTDI UPDI programmer last 2 weeks ago. So you need to go to 80 Tiny, the ones that have 3 or 4 numbers that are the new generations. So it's the same as taking, for example, this board. Well, this one is really small, but I don't know, Blink board components. Yeah, for example, and stuffing a button because this one has already an LED. Or when, for example, we can take this 80 Tiny and we have the basic board. Then this is even simpler than the older models, and you need to add it a button and an LED.
And
Is
then
that clear?
the button, again, it's not, I press the button and the LED turns on, and there's no possibility to control it. The button is connected to the microcontroller, the LED is connected to the microcontroller, and I program the microcontroller to actuate as a man in the middle. It's not, again, it's not, it always happens the same concept. Combination of circuit is we put some intelligence into the microcontroller to make it aware, let's say. And when we press the button, we can act. Yeah. It could be even a radar board if you want to call it that. Yeah, but that's the idea. So that is again at least, and as Edu said, you can take one of these boards. I'm not sharing my screen. You can take any of these boards and just add the button or the LED, or you can just get inspired by one of these and do your own from zero.
You have like the forward, so you have to connect.
Yeah. So the one, for instance, that Edu showed before, this one, you have this header here, which is for programming, but none of you made programmer for this board. And this one is for communications with your computer and power. So, and you use one FTDI cable or the HDMI board that would go here and has the USB. Let's say. Remember that we said that this board could be also a cable with the USB. So this and this are the same, but you don't use this one to program, only to communicate or to power it. And in this case of the this microcontroller, you use this header, this other one, to program it. And you use this thing for programming. But that is defined by the type of microcontroller. For the boards that you made, again, what Edu said, you normally need to use what we call 80 times series 1, which have this naming, 3216. 32 is the memory, 16 is the number of pins. And again, you have the reference here, and you can find if they are on this series or not. 412, 212, 3216, 1617, etc. And they are programmed the same with using the same board that you do. So you don't need an extra header. For instance, this one. You see here, annotate. This is FTDI for powering. That in this case, you need both of them. How is designed? Because in here you have yes, and this is the UPDI. And this one here is 2, and then 6. FTDI and 2 UPDI. Yeah. And again, you have this here. these boards here. Yes. So that's the task for the week. The important part here is learn how to use the software, make everything work, understand the workflow, start getting familiar with the components and some of the things, but learn how to use the software first. The idea is that for now, we want to keep electronics simple and software getting used to it, so that then we have the basic and we can make electronics complex and we can worry about it. Yeah. Anything else, Eduardo?
No, everything good.
Wait,
for this week, guys, you can choose any of the 80 tiny 214, 414, like, but think that even the smallest one has at least 3 left pins. That is the only thing you need. You only need 2 free pins. So you can take a small microcontroller or a bigger one. Bigger ones, you will not get any beneficial more than having to solder more pins, actually. So if I was you, personally would recommend to solder the small one, so I need to solder less pins. It will do the job exactly the same.
Yeah. The question?
Yeah. Yesterday I had so the idea is that three person or then one parts to adapt the schematic part. Sorry, the component.
No.
I have 5 pair of schematic. And yesterday I have been question that the big components operate for and
No, in principle, each, at least in the fab library, each symbol is associated with one footprint. At least in the fab library. In other libraries, what they do is that, okay, we have this symbol, and we don't put the footprint you put. We even design it or you take it somewhere else. But the idea is that, at least for us, you have to pick the symbol that already has the footprint. What I did yesterday, though, is that I deleted intentionally one footprint so that I would get the error when I import it into the PCB, but only to show how to handle the error, not as a good practice. But again, once you get to know the software, you can do also these things. But if you do these things, be careful, because then you have to document them well for other people. So when they see their board, you see, okay, this symbol says something. What is the footprint that goes with it? Yeah. But normally, in our case, each one goes with one. And it will be a matter of time. Regarding the fab and not fab and things like this, 2 things there. One is that when in doubt, and you'll see the fab, and the fab is the one that we always use. The other thing is that these components that need a value, they don't have a value per default. So resistors, they are generic resistors, and they all have the same footprint. And we just put the value in the schematic. In the PCB design, they don't have a value. It's only for our reference. And then we pick whichever one. But they all share the same footprint. Good. Should we call it?
Just a kindly reminder, please, this week, as you are doing electronics, remember to update the inventory.
Exactly. To update inventory when you get it. Is it working well for you? Does it work? Good. Okay. Finish?
Mm-hmm.
Well, thank you very much.
Thank you, Óscar.
And we'll see you around. Hope you come back soon, Edu. We miss you.